Today, we're going to talk about total quality management techniques and how we can apply these to our project management and product development activities. TQM, or Total Quality Management, involves the application of quality techniques to all segments of the enterprise. We are recommending that TQM can be applied to project management as well. Most of the project managers we have known have focused first and foremost on the project schedule, next on the project budget, and lastly on the project quality issues. After all, the cost and the schedule metrics are readily known if we make the objective. We know quickly when we are over cost or late in delivering. Everybody tells us so. Ultimately, many projects we have witnessed devolved into a nagging weekly meeting that lasted at least an hour as the PM desperately tried to assert some level of debatable control by doing a futile timeline review. We know that powerful methods exist to eliminate the flailing usually seen, particularly at the end of the project. By understanding our company and the steps we take to create and deliver the product, we improve our project's probability of successes. Hence the paraphrase of Sun Tzu: know thy organization, know thy project, 1,000 projects, 1,000 victories. My name is John Quigley. I've been involved in product development and project management for nearly 30 years. My first professional job was writing embedded code for industrial equipment using the 8051 family from Intel and subsequently a range of microchip products. I have an engineering undergraduate degree from the University of North Carolina, Charlotte, and multiple master's degrees from City University of Seattle. I have ceded 7 U.S. patents to the companies at which I have worked, and I have co-authored more than 10 books and contributed to many others, such as The Project Manager Who Smiled and the Encyclopedia of Software Engineering. I have co-authored or authored scores of magazine articles as well, and have spoken at conferences on a variety of business and technical topics around product development and project management. Consider organizations that routinely develop a set of products or services. These companies have a set of processes and are structured in such a way to deliver these products to the consumer. We will call a hypothetical version of such a company a project factory for lack of a better name. Each stage or functional area, example systems engineering, embedded engineering, and verification, will have a set of activities that are performed using some set of defined processes. The same is true for the project management discipline. In the end, we want to show how these tools can be applied to these areas to continually understand how our organization works, and more importantly, how to continually improve that performance. Now, some listeners may feel that total quality management is passé in the age of Six Sigma quality and manufacturing lean practices. Each approach has its own place. Our take on the situation is as follows. Number 1, Six Sigma is the obvious choice for cost reductions and other cost-cutting activities. Number 2, Lean is a primary tool used for waste reduction. Number 3, Lean Six Sigma is a conflation of the Six Sigma algorithm and hard money approach with lean objectives. And TQM is the approach of choice when an organization or a part of an organization desires to perform a total overhaul of the complete system. I like this quote. Progress far from consisting in change depends on retentiveness. When change is absolute, there remains no being to improve and no direction is set for possible improvement. And when experience is not retained as among savages, infancy is perpetual. A shotgun blast type of approach to improvement will lead to instability and the perpetual infancy for the organization. We do not grow or get better. In fact, things will get worse as we try. Our organization is in a constant state of tumult when we should be focusing on the work itself. Parading the flambe de jour of organization improvement methods will not lead to success. Total quality management consists of processes and a set of tools that enable us to improve a host of elements within our organization, and that includes our people without forgetting what we already know. This provides us with a continuous incremental improvement of how we do the work, especially our projects if we are sufficiently astute. Projects are not operations, although there are some similarities. There are inputs or processes and outputs from our work. There are intermediate deliveries upon which subsequent processes will work, often a continuous building of work to the final crescendo delivery. In this way, project management has similarities to manufacturing. For the project, things may not be so repeatable as we plan around the uncertainty that comes with performing non-operation work. However, there are still plenty of things that are process intensive and plenty of opportunities for us to learn about the range of possibilities that include the risk abatement to some degree. Consider if we are a product development organization. According to the Capability Maturity Model integration from the Software Engineering Institute at Carnegie Mellon, there are a number of process areas. There is a gradient of capability that goes along with each of these process areas that define the level of maturity of the enterprise. There are 5 other areas not shown on this slide, as these are project management centric. PMC is what it's called. PMC, project monitoring and control, project planning, integrated project management, risk management, and quantitative project management. You may want to check out the latest issue of CMMI for product development. Came out in 2010, I think, and is version 1.3. If you do a Google search for CMMI PDF 1.3, you will find the latest iteration. We know that manufacturing has processes, and we know there are processes associated with product development. But what about project management? Most functionally mature organizations have processes around their project management. However, even if there are few processes, the organization's work processes and intermediate work products are what produces the result of the project. For example, let us consider a product development organization where work starts with the customer input leading to requirement specification, also the start of the project scope. The customer specification writing will have an impact on the resulting project time, cost, and probably quality. Therefore, the project outcome is subject to the processes that are employed on behalf of the project. Late requirements, late project. Poor requirements, who knows what the outcome of the project would be. But for projects, we have our own set of processes. So not only does the line organization need to meet the expectation, but so too the project management organization. This is the list of knowledge areas per PMI, the Project Management Institute. Project management has a set of processes also. These processes, coupled with the knowledge areas, are then fodder for analysis, for understanding, and improvement. Product requirements come from a variety of places. The sources of our requirements can be legal or specific to industry origin. The customers can be internal and external to the company. For example, the manufacturing portion of our company may have specific requirements on how the product is to be put together. We may have requirements based on the capability of our pick and place machines or reflow ovens. These requirements are in addition to the requirements from the end customer. Some requirements point to other requirements. For example, the life expectancy from a battery operated unit and the weight of that unit. These 2 requirements may point to a certain battery technology for power density and size. Capturing requirements is not a simple matter. Both requirements and scope elicitation requires attention to prioritizing and balancing of the many demands from both internal and external customers. We have to know what is really meant when we ask questions of our customers. This requires interviews and clarifying follow-up questions until we achieve a mutual understanding. If we do not already know the sorts of stimuli to which the product will be subjected, we may have to learn this information through field studies. We can have competing requirements such as the cost of the product and the number of features or the weight and the battery power required. Product requirements set the stage for the project. The stability of requirements tells us something about the risks to which the project may be subjected. According to IEEE Standard 830-1998, a recommended practice for software requirement specifications, the characteristics of good SRS requirements are correct, unambiguous, complete, consistent, ranked for importance, verifiable, modifiable, and traceable. These requirement attributes begin to set measurable items for the project scope and as such items for our TQM tools. We may select metrics from the requirements gathering and documentation phase that can give us some indication as to the stability of the scope of the project. I know some of you are saying it's enough to do the job. Measuring takes additional time and effort. In many cases, much of the measurement gathering should not be so difficult. On the other hand, if we do not measure, we have no idea where we are in the continuum of project and enterprise accomplishment. If we are conducting a project, then, without metrics, we neither know where we are or what it takes to get to where we desire. The project manager should enforce metrics acquisition from the onset of the project and never let up. The only time metrics capture should stop is for a specific metric, and only if that metric has been clearly shown to be meaningless. If we start off well, then we increase the chances we will finish well. When we aggregate these metrics, we are able to say something tangible about the organization and the project in particular. We have already articulated the philosophy of TQM. Here is the process and fundamental tools associated. None of this is math intensive or complicated, with perhaps the exception of control charts. In plan, we establish objectives, that is, the specific actions we will take to improve the process. However, to do that, we must have an idea of the improvement areas, and that is the reason for the metrics. Do. We execute a plan and we perform the process. Check. Compare against expected results. Deming used the word study as he thought this focused more on the analytical aspects. Act. If the check shows that the plan that was implemented in do is an improvement to the prior standard, it becomes a baseline. Then that becomes the new standard for how the organization should act. If the check shows that the plan that was implemented in do is not an improvement, then the existing standard will remain in place. In either case, if the check showed something different than expected, whether better or worse, then there is some more learning that has to be done. This may seem targeted to the quality manager for the enterprise, but it is critical that the project manager understand the use of these tools. For example, one of the most powerful, useful tools is the Pareto chart. A project manager could use this plot to analyze which customer complaints are most frequent during a project, or perhaps look at complaints from the point of view of cost in currency or in time. While the tools are traditionally or typically applied to manufacturing endeavors, these same analysis tools can be applied to both line management as well as project management activities to enable better control over the project. To be able to improve either, you will use the set of TQM tools. A Pareto is effectively a sorted bar chart or sorted histogram. The great frequency will be on the left and the least frequency of occurrence will be on the right side of the chart. The purpose of the Pareto is to quickly identify those items that are significant, and in so doing, simultaneously identify those items that are not currently significant. The so-called 80-20 rule comes from this plot. For example, we often observe that 20% of our customers provide us 80% of our revenue. The Pareto chart can induce distortions in our understanding when we chart information that is not truly relevant. For example, suppose we simply chart frequencies of issues with regard to returned warranty products. Frequency may not be nearly as revealing as making a Pareto chart of the cost of each issue. The frequency chart may give us a clue to the most important niggling problem, but it will not enlighten us as to the product giving the most financial pain to the customer. The Pareto chart can induce distortions in our understanding when we chart information that is not truly relevant. For example, suppose we simply chart frequencies of issues with regard to returned warranty products. Frequencies may not be nearly as revealing as making a Pareto chart of the cost of each issue. The frequency chart may give us a clue to the most important niggling problem, but it will not enlighten us to the product giving the most financial pain to the customer. Consider the Pareto chart of failures witnessed with an instrument cluster for a particular vehicle. We see the best place to start the investigation and fix in terms of number of failures is with the speedometer. We would then set up some exploratory testing to understand why this is so. However, just because the problem or failure is more prevalent than others may not mean that the money at stake or customer impact is the largest. When we know what the returns cost, including our handling of them, we can rework the Pareto chart to illustrate the dollars at stake and not just the number of units. In this case, we see that the dollar amount associated with the failures follow the number of failures closely. We can then use this information to determine our plan of attack to improve the situation. Even with recognized distortions and limitations to our Pareto charts, they form one of the most significant decision support tools we have. In general, the 80-20 concept is easy to explain to upper management and provides a good support for our decisions. If our project management office retains historical data of the issues discovered during the course of numerous projects, and they should, we can plot the frequencies of issues we have seen and generate a Pareto chart of undesirable project or project management behaviors. Once we know who the heavy hitters are, we can begin to train out or introduce corrective actions that eliminate or reduce the most common issues. We suspect putting a dollar value on project management issues may not be worth the effort, and hence we are willing to accept some potential distortion in our understanding. This is a story about a special project to produce a unique vehicle for a show. The development work has largely transpired. The project manager has put together a schedule to meet the expected delivery but is unaware of some key information. He meets the verification group manager and informs him the date the test specimen will arrive and that test should be able to commence on the following day. The histogram is similar to the Pareto chart in that it provides a graphical representation of data frequency. However, the histogram has no requirement that the data be sorted from most frequent to least frequent. The histogram has been around for more than a century and was created by Carl Pearson. The histogram will sometimes present data in a specific order on the x-axis, in this case the amount of time required to turn a proposed test specimen to a suitable test subject. This data on the abscissas is usually collected into intervals called bins. In this instance, the data is divided up into days. The ordinal y-axis represents the frequency of count data that appears in that interval. Therefore, multiplying the number of bins times the frequency for each bin, adding them all together gives us the total of the collected data or counted data. In this graph, we see a distribution of vehicle preparation time. The project manager may believe he has a chance at making this meet their schedule, but there is no instance of test preparation taking 1 to 2 days. In fact, to accommodate this aspect of the project manager would need to have allocated enough time for this preparation to improve their odds, perhaps more like 13 days, or determine the reasons why the graph looks this way and solve those root issues. Knowing the limitation of the start date, we are then able to ask questions as to why this may be the case. We can perform a Pareto analysis of the failures associated with the delivery, that is, those things that must be corrected before we are able to start testing. This is a Pareto of the corrections that take the most amount of time to correct. This could have easily been used specifically on project data. For example, cost may be with categories such as human resources or rework or PM time or outsourcing material, those kind of things. We can dig further still to determine the specific trouble areas that inhibit our ability to immediately start testing. Okay, so this little foray was a little more in the realm of management, but that impacts the project's ability to deliver, and it is incumbent on the project manager to have some understanding of how the test processes work, and more importantly, how to understand what really happens and why. What is more important is that this demonstration could be easily extrapolated to project management. Let's go back to our scope discussion. There are things that happen there, changes, alterations, parts missing, that would be good to understand and improve over time. We will leave Pareto now and move on to Ishikawa or fishbone diagram, or cause and effect diagrams. This tool is used to generate ideas for determining the root cause of a malady. Therefore, it happens after the fact. Typically, the diagram is laid out using 7 M's: measurements, materials, manpower, Mother Nature, methods, and machines. That's how you would do it in manufacturing. At the head of the fish is the failure mode. In this instance, it is surface flaws. This could be any failure that we have observed, including project management failures. Each major line off the label according to one of the 6 M's above. And there are individual lines coming off each of those with the things that can go wrong with that bone that will produce the errant output. For example, under machines, we have sockets, bits, machine speed that contribute to the surface appearance. Let's take a look at Ishikawa toward project endeavors. In this case, we put our project failure issue at the head of the fish, and we have each knowledge area off of the backbone. I suggest you pick something and walk through a theoretical failure. You may be surprised at just how all these knowledge areas are connected and how any of these impact the outcome. For example, we have a schedule failure at the head of the fish. This failure is brought about because of an unclear or drifting scope of the project. It can also be born out of insufficient or inappropriate communications with the customer, or perhaps we're missing significant talent to ask appropriate questions. You would then devise subsequent actions to figure which one of these are contributing the most, probably a Pareto analysis to understand the distribution. A checklist is an ordered table of activities or items that need to be completed or acted upon. In the most primitive case, we can create handwritten checklists and literally check off each item. One of the great features of a checklist from the project management aspect is that the project manager can nearly completely control the actions of a project team member through the use of exhaustive checklists. In fact, the work breakdown structure is a hierarchical checklist of the tasks and deliverables for the project. We have seen checklists used to provide objective evidence on the state of a project for stage gate reviews. If parts of the checklist are missing, a judgment is made as to whether the infraction inhibits passing the gate and moving on to the next stage of the project. Of course, there are limits to checklists, and one limitation is the level of detail of that item itself on the checklist. What constitutes success or achievement of that item on the checklist? For example, we check off design review, where we had few people participate with insufficient time with the documentation prior to the review. It is difficult to glean all of that information from a checklist item labeled design review. Would that constitute closure of this item on the checklist? If we track our steps to do the work, we can also assess the impact of skipping those steps on the outcome. We start by identifying the steps like any other checklist. Then we weight the checklist items, objective against the reason for doing the task. In our first line, we have quality function deployment activities, and this company identifies this activity supports the quality and the feature content of the product, though predominantly the quality of the product. In this slide, you see that the QFD work was done, but it was conducted late, and under these conditions, the team considers the QFD work to be less than optimal, but not without worth. So they receive 50 points. In this slide, you see that QFD work was performed in accordance with the expectation set out in the organization process document. And under these conditions, the team considers the QFD optimal. Scatter plots help us understand correlation between two variables. That is, correlation and not causation, though it could be causation. A positive correlation means that a positive change in one variable and a positive change in another. The tighter the pattern, the more of a correlation. A negative correlation means both variables decrease. If we are building software product, we can plot iterations of the product against level of completeness. Schedule Performance Index compares our actual schedule accomplishment to that of our plan. In this table, we view organization A, and here we're looking at SPY for another organization. Can you tell me which one of these was better? Now consider this view of both organizations' schedule performance index capability. It is certainly easier to see the quality of the supplier. The first supplier, B, we are especially interested in the dispersion. There is a small collection of projects with numbers that appear to be much different than the others. Now look at the other supplier, A. There is a clear preferred supplier in this regard. We see that the variation in the collection of projects over time is better than in the previous organization. The variation among the measurements of the projects over time is much tighter, or less. We can use control chart ideas for monitoring our cost performance index. CPI is the ratio of our planned cost to the actual expenditures. We can see the variance in the weekly reports and see how that impacts the average in the running average report. This gives us some idea of the measure of performance and perhaps when not to overreact to fluctuations in the performance that may seem large but in fact are not intolerable. We can monitor our schedule performance index over time as a control chart. The calculation for the upper and lower control limits can be found anywhere online, and in fact, there are YouTube videos dedicated to this calculation. Even if we do not perform the math shown in the following slide, we can set our expectation upon the limits and use the tool as a risk identifier. Rather than have a hard, fast number by calculation, you decide to use this as a risk measuring tool, saying I will take action when SPY goes below 95, for example, or above 110. Even when we have organization-defined processes, we sometimes have to alter to fit the specifics of the project. Flowcharts like this change management description show how the project will intend to work and provide some measure of repeatability, especially when we are altering from our typical or normal mode of execution. If we are a stage gate organization and we track organization's ability to pass gates on time and meeting the defined objectives, we can use a running average chart for this, or we can use statistical analysis techniques to better understand the variance. Once we see gate passing rates do not meet how we wish to perform, we can dig in further by identifying the objectives that failed using Pareto analysis or ordered bar graph techniques. Once we know the types of failures, we can start uncovering the source areas, which will give us clues as to the specific actions we will need to take to remediate. We may need to use brainstorming techniques, in which case Ishikawa or fishbone diagrams can help us explore what we think might happen through thought exercises, as it were. Though projects are unique, our methods of executing usually have some basis in process, which means we can treat our project execution as a factory. We can apply these tools to the PM function as well as the line management functions to better predict and rationally improve. Thank you for listening to the video. Any questions, please contact me at john.quigley@valuetransform.com. You can leave them here on YouTube, or you can visit the Value Transformation website, www.valuetransform.com, and visit one of the discussion boards. We'll be happy to continue the discourse.